Okay, hello and welcome to today's lecture. We're going to start chapter 13 today. Chapter 13. We're going to talk about vector functions. Vector functions, eventually, they're going to be repeated in Math 1D. There you learn how to find the limit, find continuity, taking the derivatives, and finding the integral of vector functions that you learn in chapter 13. Very well. 13.1, page 1. So where does vector function come from? Very well. Think about it this way. Remember, recall. For a position of an object or a particle, we said that, okay, this position is defined by x and y. X representing the x coordinate, y representing the y coordinate. That makes sense. You could just graph this and say, hey, this is x, this is y, and you follow a pattern, a line, a curve to follow the position of that object or particle. Then we said that we're going to define a new variable like time, like heat, and connect x and y to that new parameter. We define it this way, x, t, y, t. And we saw that x and y are functions of t. Now we generalize the idea to three-dimensional space and we say that, hey, now we take all of these components, all of these coordinates, and define functions for example, the position of that particle. So definition of vector function. The definition is very easy. A vector function or a vector value function, a vector function is defined as, for example, you can take R, you can put a little bar on top of it to show that here we have a vector, and we say that this vector depends on parameter t, and we define it this way. Since we are using a vector, we're going to use a vector symbol. The first component is going to be a function. So suppose we use f, which depends on parameter t, comma, the second component, another function, g depends on parameter t, and finally, the last component, the third component, is going to be a function like h depending on variable t. So as you can see, all of these are functions. F is a function, G is a function, H is a function, and so on. So R bar as a vector depends on three functions. Of course, you can generalize the idea, define a vector function in 4-dimensional space, 5-dimensional space, and dimensional space. Okay, guys, since you have a function, this guy is a function, of course. This is a new function. Definitely, you can find the domain of the function. You can find the domain of the function. You can find the range of the function. You can take the limit of the function. You can take the derivative of the function. You can graph your function, and so on. Since it's just a function. Let's go over one example to see what's going on. So you're still on page 1. Example says, hey, we have a vector value function, RT, which is defined as, your first component is given as t cubed. The second component is defined as ln of 3 minus t, and the last component is function square root of t. Very well. Okay, this is your f of t. This is your g of t. And this is your h of t. This vector value function is vector function consists of 3 functions. Okay, guys, we're going to graph our vector function. So here we select, let's see, vector field. If we use vector field, you need M, N, and P. I don't think that works. We're going to try it later. Let us use a vector here. It doesn't give you that, so let me find, okay, something nice to work with. Space curve, no, I don't need a space curve. Parametric surface, it's not that. Okay. Space curve, maybe. Okay. So the first one is t cubed. The second one is ln of 3 minus t. And the last one is square root of t. So let's write t raised to a half. Okay. So I don't need this. I don't need this. And here. So this is the graph of this vector function. Okay. So let us talk about the limit of our function. So let RT be equals to f of t, comma, g of t, comma, h of t be a vector function. The limit of this vector function, while, for example, t goes to, let me follow the note, t goes to a is equal to, so of course it has components. You take the limit of each of these functions, so you have limit of f, limit of g, and limit of h. Limit of f, while t goes to a, limit of g, while t goes to a, comma, limit of the last function, h of t, while t goes to a. This is the limit of vector function. And note that the limit for each of these must exist. Otherwise, you say that the limit doesn't exist. So the limit of this function depends on the limit of each of these components. Note that the limit of vector function depends on the limit of f, G, and H. For example, take a look at this example. So what do we have here? R of t, your vector function is defined this way. 1 plus t cubed in the direction of x-axis, t e to negative t in the direction of y-axis, and sine t over t in the direction of z-axis. Question says, well, find the limit of this vector function while t goes to 0. What is this limit? Very well. Since we have a vector function, it has 3 components. The limit of this vector function depends on the limit of each of these. Okay. It's equal to, so for simplicity, let's write it this way. The limit of 1 plus t cubed as a polynomial while t goes to 0. You don't have any problem with this. Since it's a polynomial, it's continuous everywhere. You just plug in 0 and you're done. Come. The limit of your second function, the limit of t divided by e to t while t goes to 0. For this guy, we don't have any problem because our denominator is e to t. E to 0 is equal to 1. 0 divided by 1 is just 0. And comma, the limit of sine t divided by t, we all know that that limit is just 1. Okay. So since 1 plus t cubed is polynomial, this is equal to 1 plus 0 cubed. Since we have 0 divided by e to 0, 0 divided by 1 equal to 0. This is just so here, 0 over e to 0, comma, and here you have limit of 0 over 0. You can say that, hey, I can apply L'Hopital's rule. Since we have 0 over 0, we get cosine t divided by 1, while t goes to 0. So this guy is 1, this is 0, and this is just. This is the limit of your vector function. Okay, guys, take your time, write this down. So our first component is 1 plus t cubed. So 1 plus t cubed. The second component is t divided by e raised to t. The last component is sine t over t. Okay, you're missing parameters. Okay, so let us put everything in parentheses here. Maybe that works. Oh, okay, I see. Sine t. Very well, this is your function. Vector function, let us just use negative 2 pi. Okay, perfect. So we are expanding the domain. There you go. Let's see what we have. So we are still on page 2. We're going to talk about continuity. As usual, when you have a function, you can discuss all of those properties for a function. So a vector function like R, T is continuous at a point T equals to A if, first of all, A belongs to the domain of the function. So A belongs to the domain of the function. Limit of the function exists at A to limit of the function exists at A. It means that all of those components, F, G, and H, they have limit at A. And finally, the limit of function while T goes to A is equal to the value of the function at A. So this is pretty much the same as definition of continuity for a function in one variable. So equivalently, you can say that a vector field, a vector function is continuous if and only if F, G, and H are all continuous. So since R depends on F, G, and H, continuity of your vector function R depends on the continuity of all of these components all together at the same time. So if one of them is discontinuous, you say that, hey, my vector function is discontinuous. Definition of space here. The set of all points, x, y, z, such that x is equal to f of t, y is equal to g of t, so the first coordinate of the point, the second coordinate of the point, and the last coordinate of the point, is denoted by C, and we call it space curve. It's called space curve. So what we did so far using a computer and an online 3D generator is actually looking at the space curves for vector function. Let's go over one example. Talk about space curve. Parametric equations for space curve or your vector function. So we are on page 3 now. Example. Suppose you have a vector function. Let your vector function is defined as RT. Here you have 3 components, 1 plus t, comma, 2 plus 5t, comma, -1, plus 6t. There we go. It says describe the curve. Okay, guys. Let us take a look at our graph. So our x is 1 plus t. Our y is 2 plus 5t. And our z is minus 1 plus 60. As you can see, the space curve is just a line. Of course, this line continues both sides. So if I just write negative 100, positive 100, it's going to continue. You can just minimize this, and you can see this is just going toward left and right hand side. It continues to both sides. And as you can see, this vector function is continuous everywhere. The domain is negative infinity to positive infinity. The limit of the function at any value of t is equal to the value of the function. Okay, so we already visualized this graph, and now we want to see algebra behind it. Let's get back to previous chapter. Previous chapter, we talked about lines and planes. Here we go. Here you have RT equals 2. So you have constant 1, constant 2, constant negative 1. I'm going to take these constants and write them outside the vector. So you have 1, 2, minus 1, plus t, 5t, and 6t. Of course, you add two vectors, and you can form this new vector, which is just a vector function. Here, I'm going to factor out t. My rt is equal to 1, 2, negative 1, plus t times. Now I'm forming my v, if you remember the directional vector, 1, 5, and 6. So this is your point, this is your parameter, and here you have your direction. So this is actually parametric equation of a line. Sorry, this is vector equation of a line. We can write it as a parametric equation by just rewriting this side as the components. Very well. Another interesting example for you. Still on page 3. So R of t is defined as cosine t I plus sine t j plus t k. The first component is cosine function f of t. The second component, sine function g of t, and the last component is just t, h of t. So as you can see, the domain of this function, is R. T can be any real number. Cosine is continuous everywhere, it's a nice function. Sine is continuous everywhere, it's a nice function. And t is also a polynomial, so it is continuous everywhere, and the domain is the domain of all of these, the intersection between them. So it's going to be just R. And of course, this line is continuous everywhere. RT is continuous everywhere since F, G, H are all continuous on R. Okay, let's take a look at the graph of the function. Then we're going to talk about the algebra behind this. The first component, cosine. The second component, sine. And the last component is t. So let me put this t in parentheses. There we go. This is the graph of your function. Let me just add these to 2000 to get it more smooth. This is the graph of this vector function. Now, what if I restrict this to two-dimensional space? What do you see here? If we just restrict the graph to x, y plane, what you see is just a circle. There you go. So, my x coordinate is cosine t. My y coordinate is sine t. What's the relation between x and y, cosine and sine? We know that cosine squared plus sine squared is always 1. It means that we can form a circle. So
they have to commit to one. There's 3 of them.
There you go. So if you do the algebra, you can actually see if you restrict yourself to x-axis and y-axis or xy plane, you can form cosine squared plus sine squared, which is equal to 1. So by taking the first coordinate and the second coordinate, we have just a circle in xy. This is x, this is y, and we have a circle. But note that by adding a third function, which is t, along with z-axis, we are taking this circle and we're just stretching this. And as you saw in the graphing website here, if we just forget about two-dimensional space, you're having a helix, a vector function that continues, and it continues to both sides of z-axis. Let us move on to page 4. Go over other examples. Page 4. Question says, you have 2 points, find a vector. Equation or vector function for line passing through these 2 points. The first point P 1, 3, and minus 2, the second point, 2, negative 1, and 3. Okay, first of all, let us connect these 2 points and write equation of line segment connecting these 2 points. The equation of line segment connecting these 2 points follows the formula RT equals to 1 minus T, the initial point, like R sub 0, plus T times R sub 1. So initial point and end point. Initial point and terminal point. So suppose you take P as the initial point and Q as the terminal point, just plug them in and write down the equation. So this equation, 1 minus P. So since our initial point is now written in vector language, P, if you connect P to the origin, we can form a vector. We can write it this way. 1, 3, minus 2, plus T. The terminal point is now converted into a vector connected to the origin, which is 2, negative 1, 3. That's why we changed the symbol to a vector symbol. Very well, let's simplify this guy. Here you have 1 minus T, comma, 3 times 1 minus T, comma, minus 2, 1 minus T, plus 2T, negative T, 3T. Let's combine all of these together. Here you have 1 minus T plus 2T, comma, 3 minus 3T, the second component, minus T, and I'm distributing negative 2 here, minus 2 plus 2T, and I'm adding that to the last component, which is 3T. Okay, my vector function is equal to T plus 1, T minus 4, 3 minus 4T, and here I have minus 2 plus 5T. Very well, let us graph this. The first component, T plus 1. The second component, 3 minus 4T. And the last component is minus 2 plus 5T. Very well. Here's our graph. Space care for this vector function. It's just a line. We expect this to be just a straight line. We just wrote down the equation of the line, and we expect our graph to be just a line. We can restrict it to 2-dimensional space, and as you can see, this is a line passing through x-axis. We are on page 5, and we have an example. So this example says find a vector function. Find a vector function that represents a curve represents a curve of the intersection of cylinder. This cylinder has equation x squared plus y squared equals to 1, and the plane y plus z equals to 2. So what are we doing? You're taking a cylinder. You might say, hey, professor, it's not a cylinder. It is x squared plus y squared equals to 1. It's just a unit circle. That is true if you are in two-dimensional space. So in two-dimensional space, this is just a unit circle. It is a unit circle. In three-dimensional space, what are you doing? You're taking this unit circle, x, y, z, and you're just building that up. So this is like this. Here you have your circle, unit circle down here. Then you continue building the unit circle on top of each other. Then you form a cylinder. And so upward and down. So in three-dimensional space, you have a cylinder. As you all know, this is y plus z equals to 2 equation of a plane in three-dimensional space. If you just consider y z plane, of course it's a line. But in three-dimensional space, this is just a plane. Okay, let's begin. Find a vector function of intersection between these two. Let's graph this together, see what's going on. So you have x squared, y squared, okay, let's see. So let us write it this again, it doesn't make sense. Okay, let me use a different graph. Y squared plus c squared equals to 1, and this is a plus sign. So this is the first one, okay. So as you can see, here you have just a cylinder. And let me add another implicit surface for you. This is y plus z equals to 2. And here you have your plane. So this is the intersection between these two. Now if I change this to z squared. Okay. Perfect. Here we go. So we want to find equation of this vector function, the intersection between this plane and cylinder. Okay, so what I'm going to do, I'm going to take my cylinder. So let us start. by x squared plus y squared equals to 1. I know how to write this using parameter. X can be written as, for example, cosine t. Y can be written as sine t. Of course, parametric equation. Or you can just take x equals to sine t, y equals to cosine t. So you know that x is cosine and y is sine. Now, for the plane we have y plus z equals to 2. We don't have any equation, parametric equation for z. We're going to use y to write this equation for z. So z is equals to 2 minus y, and I already know that y is sine t. Okay, let's use it. My z is now 2 minus sine t. Very well, I have my vector function rt is equal to cosine t, the first component, the first function, sine t, comma, 2 minus sine t. Here we go. And note that your t ranges between 0 to 2 pi, so you can add that here. Make sure we have everything written here. 2. Very well, let us start 13.2. We're going to talk about the derivatives of our functions. Page 1. Very well. The rate of change or the derivative of your function of vector function R t. So as usual, we use the limit definition of the derivative of a function. dr dt, or just simply r prime of t is equal to the limit of r of t plus h minus r of t divided by h, while h goes to 0. As usual, if you have a nice function, like a polynomial function, a trig function, exponential function, you can use those little shortcuts to take the derivative of the function. So note that when we have nice components. What do I mean by that? Polynomial functions. Polynomials. Sine, cosine, exponential, and so on. We can use the shortcuts to take the derivative instead of using the limit definition. The limit definition of the derivative. So we have a theorem. Let's write down the theorem here. RT equals to f of t, g of t, and h of t be a vector function. If all these components, f, g, and h, are all differentiable, what do I mean by that? It means that the limit of f of t plus h minus f of t divided by h while h goes to 0, and the limit of g of t plus h minus g of t divided by h while h goes to 0, and the limit of h of t plus h, this h is different, so let's write it this way. Distinguish this between that h in the limit definition minus h of t divided by h while h goes to 0. All of these exist. Then the derivative of your vector function is equal to derivative of f, derivative of g, and derivative of h. So the rate of change of the function is r prime. If you take the derivative of the function and divide it by its magnitude, you get a unit vector. That's how we learned before. Recall that. For a vector v divided by the magnitude of v is always a unit vector. Unit vector. We're going to do the same thing here. Let RT be a vector function, so it is obviously a vector. R prime of t be its derivative. We take the derivative r prime of t and we divide it by its magnitude. R prime of t, the magnitude. This is definitely a unit vector, and we call it a tangent vector, which is unique. So here you have the notation that we use is t. T is a vector, definitely a vector, and this is called a unit tangent vector. Okay, let's go over one example. Page 2. So we have our unit tangent vector. Example. Question says, find the unit tangent vector. Find the unit tangent vector to your vector function is defined as r of t. Let's specify the parameter 1 plus t cubed, comma, t e2 minus t, comma, sine 2t at t equal to 0. Very well. So let us form the tangent vector, unit tangent vector. Let's follow the formula. This is equal to the derivative divided by the magnitude of the derivative. So here you have the derivative of the function, 3t squared, comma. For this guy, you have to use product rule. So the derivative of t is 1 times e to minus t plus the derivative of e to negative t, which is minus 1 e to negative t times t, comma. Here you have, you're using chain rule here. You get 2 cosine 2t divided by the magnitude. What's the magnitude? This is square root of the first component squared. So you get 3t squared raised to the second power plus this guy squared. So e to negative t minus e to negative t times t squared plus the last component raised to the second power. Luckily for us, we know that t is equal to 0. So we can just plug that in and simplify as much as we can. Here we go. So the first element is 0. The second element is 1 minus 0, which is just 1. And this by cosine of 0 is just 1, so you get 2. Divided by square root of 0 plus 1 plus 4, which is square root of 5. So you can write this guy as 1 over square root of 5 times 0, 1, 2, 4 square root of 5 divided by 5, you can rationalize it, times 0, 1, and 2. Both of them are good. Very well, another example for you. So this example says, RT, your vector function is given. This vector function is square root of t, comma, 2 minus t, and the last component is 0. So you can actually easily graph this in two-dimensional space. It says find the tangent vector at t equals to 1. Okay, guys, it doesn't say unit tangent vector. It just says the tangent vector. Note, it does not say unit tangent vector. It's not saying that find t of t. Just says find tangent vector. To find tangent vector, we just take the derivative of this function. To find the tangent vector, we find a simple find r prime of t. Okay, let's take the derivative of this function. R prime of t is equal to the first component, 1 over 2 square root of t, and the second component is negative 1, and the last component is just 0. You can add it here, or you can just forget about it because it is just 0. So this is equivalent to 1 over 2 square root of t in the direction of x-axis minus 1 times j in the direction of y-axis. We found the tangent vector. It says find tangent vector when t is equal to 1. So this is our tangent vector. R prime at 1 is equal to, so just plug in 1 over 2 and negative 1. Okay. So note that when t is equal to 1, r of t, so just note that. When t is equal to 1, the position of your vector function is square root of 1, which is 1, 2 minus 1, which is 1. 1 and 1. 1 and 1, your vector is a half and negative. Okay, let's graph our function. Here you have your function here. Square root of t, 2 minus t. Okay. By point plotting, you can easily graph this function. If t is equal to 0, then the first component is 0, the second component is 2. So 0 and 2. If t is equal to 1, you get 1 and 1. 1 and 1. If t is equal to 1, you get 1 and 1. And if t is equal to 2, you get square root of 2, 1.4 and 0. So it's going to be here. So just put this down here. This is the graph of your function. This is your r of t. Some part of rt. Very good. When t is equal to 1, the point or the vector on the graph is 1 and 1. So 1 and 1 is here. Since it's a vector, so we connect that to the origin. This is 1 and 1. Very good. At 1 and 1, your tangent vector is a half and your y is negative. Guys, here you have a tangent vector in the direction of negative 1. So this is your tangent. This is r prime of t. Tangent vector. Let's move on to the next example. Question says, find equation of tangent line to the helix x equals to 2 cosine t, y is equal to sine t, and z is equal to t at point 0, 1, 0, 1, and pi over 2. Very well. To find equation of any line, what do we need? We need the starting point plus t times the directional vector. This directional vector is your tangent vector. Direction vector is r prime of t. So at the given point, so let's add all the details. Very well. So what's given? The point is given. You have your vector function. The vector function is RT equals to 2 cosine t, sine t, and t. So v, or the derivative, is equal to minus 2 sine t cosine t and 1. Okay, so what is t? So keep this one here. To find the t, look at the question. Question says z is equal to t. The last component is pi over 2. Z is equal to t, and z is equal to pi over 2. So t is pi over 2. You could say, hey, y is sine t and y is 1. Sine t is equal to 1. I'm going to solve it. If you solve it, t is again pi over 2. You might also say that, hey, 2 cosine t is x, and x is equal to 0. I'm going to set these two equal to each other and solve it. 2 cosine t is equal to 0, cosine t is equal to 0, t is pi over 2. So you can use the first component, the second component, or the third component to find your t. So t is equal to pi over 2. We're going to use this to find v. So negative 2, 0, and 1 is my vector. Okay, I'm going to get back to the equation of the line. I'm going to plug everything down here. So equation of the line, tangent line. So this is tangent line. Is equal to, the beginning point is equal to 0, 1, pi over 2 plus t times v, which is negative 2, 0, and 1. So equation of the tangent line, we can write it as 0 plus minus 2t, so minus 2t, comma 1 plus 0, and here you have pi over 2 plus t. So your x is minus 2t, your y is 1, and your z is pi halves plus t. Let us move on to the next page. Page 3. We have an example here for you. This example says, show that if the magnitude or norm of your function, vector function, is constant, so if the magnitude or norm of the function is fixed, is equal to a constant, then the tangent vector is orthogonal to the curve of the function, to the graph of the function. There you go. Okay. So we call that two vectors like A and B are orthogonal or perpendicular to each other, if and only if their dot product is equal to 0. Also recall that the magnitude of a vector is defined as square root of the first component raised to the second power, the second component raised to the second power, and the third component raised to the second power. So if I square both sides, I get magnitude or norm of a vector raised to the second power, which is equal to a1 squared, a2 squared plus a3 squared. What is this? This is a times a. So the magnitude raised to the second power is a, the dot product between a and itself. A dot a. So this is my vector. A1, A2, A2. I'm going to use these two facts that I already know. Okay, what I have here, I know that I have a vector with a fixed magnitude. So I'm going to use this fact here. Since magnitude of R is fixed, it means that the magnitude squared, which is A times A, is equal to C squared magnitude of R squared. This is just a number on the left hand side. I'm just raising both sides to the second power. And this guy is equal to the dot product of A times A, or RT times RT. RT times RT equals to the constant C squared. Now what I'm going to do, I'm going to take the derivative of both sides. Now, take the derivative. So since I have the dot product multiplication, I'm going to apply product. So the derivative of R times R plus R times the derivative of, and the derivative of constant is always 0. So what do you have? Since you have a dot product, you can switch these two. You get 2 times R prime dot R equal to 0. So a product between these two. And if I divide both hand sides by 2, I get R prime times R equal to 0. What's the meaning of that? It means that the dot product between two vectors is equal to 0. So R and R prime, they are orthogonal or perpendicular to each other. Page 4. There you go. Let RT be a vector function. Suppose capital RT is the anti-derivative of vector function RT. Then the integral of RT dt while t ranges between a and b is equal to RB minus R Very well, let us go over one example. This example says, suppose your vector function is defined as 2 cosine t, sine t, and 2t. Very well. It says, find the integral of RT. And then part B says, find the integral of RT while t ranges between 0 to pi over 2. Okay, perfect. So we'll go for the dt. So we take the integral of the first component, 2 cosine t, which is 2 sine t, in the direction of x-axis, plus the integral of sine, negative cosine t, in the direction of y-axis, plus the integral of 2t is t squared in the direction of z-axis. We can add the constant of integration at the end. Very well. We found the antiderivative of this function. This is your RT, capital R. Now for the second part, you have upper limit and you have lower limit. You just need to plug in upper limit, plug in lower limit, do the subtraction. Okay, if I plug in pi over 2, I get 2 sine pi over 2 in the direction of x-axis plus negative cosine of pi over 2 in the direction of y-axis plus pi over 2 squared in the direction of z-axis minus 2 times sine of 0 in the direction of x-axis plus minus cosine of 0 in the direction of y-axis plus 0 squared in the direction of z-axis. Okay, let's simplify. The rest is just algebra. This is equal to, so the first vector is 2, 0, pi squared over 4, minus the second vector, which is 0, negative 1, and we can add these, in this case subtract these two, and we get 2, 1, and pi squared over 4. This is your integral.